In today's video, I'll give you a straightforward rundown on inertial measurement units, or IMUs. We'll cover the various sensors involved in an IMU and delve into how these components work together through a method known as sensor fusion. Let's kick things off with a hands-on demonstration. Here's an IMU with integrated sensor fusion. As I manipulate the IMU, it gathers data from its sensors, runs this through fusion algorithms, and then transmits the results to a Unity program via USB. You can see the model on the screen mimic the movements. Now that we've seen what an IMU can achieve, let's examine the sensors that constitute an IMU. Smartphones and smartwatches typically use three types of motion sensors: accelerometers, gyroscopes, and magnetometers. Together, these form what's known as an IMU. The data these sensors collect is synthesized using complex calculations to provide useful features like screen orientation, device heading, and gesture recognition. These sensors have a history predating modern computers. Gyroscopes have been crucial in aviation safety for more than a century. Accelerometers initially monitored earthquake tremors, and magnetically based compasses have guided ships for millennia. What's changed recently is the application of microchip manufacturing techniques to these sensors, making them incredibly small and cost-effective. For developers, the most straightforward interaction with these sensors is through smartphone apps. Phones come equipped with these sensors, allowing apps to access their data directly. At Fidgets, we produce high-precision motion sensors for when you need greater accuracy or prefer not to use a phone. Our sensors are quick, precise, and compatible with major operating systems and programming languages. We also provide ready-to-use software for testing and visualization. Next, we'll explore each sensor individually, starting with accelerometers. An accelerometer measures acceleration very accurately. For example, as I sit here, gravity pulls me down while the chair counters this force. That's 1 g of acceleration, which the accelerometer next to me also detects. If you were skydiving, you'd feel weightless during freefall, and your phone's accelerometer would show 0 g. Conversely, accelerating in a sports car makes you sink into your seat, a sensation the accelerometer can quantify. Gyroscopes, meanwhile, detect rotation. Even if I'm blindfolded and spun in a chair, I can feel the rotation, something gyroscopes can measure more effectively without getting dizzy. Lastly, a magnetometer measures magnetic fields, with the common compass being a specific application that determines direction by assessing Earth's magnetic field. However, each sensor has its drawbacks, which is why they are often combined through sensor fusion. While an accelerometer can get confused by jittery movements, it quickly recalibrates when still. Gyroscopes might drift over extended periods but are incredibly smooth and precise for short durations. Compasses are susceptible to interference yet can swiftly recalibrate to north once disturbances cease.